Hello, today we're going to review Unit 2 for the AP Chemistry exam. Unit 2 has to do with bonding. So we're going to review some free response questions and then some multiple choice questions related to Unit 2. Okay, so let's start on the first free response question here. It wants us to draw the complete Lewis electron dot diagram for ethine and the appropriate cell in the table above. This is a little small. I'm going to draw it over here, but remember when it tells you to draw it or graph something, do it in the appropriate spot where they tell you to do so. But for this one, C2H2, you need to make sure that you're using valence electrons. Carbon has 4 valence electrons and hydrogen has 1. So when I draw this, I'm going to use the simple method for drawing Lewis structures first. Carbon has 4 valence electrons and hydrogen has 1. So in order to make the structure work, I'm going to connect the dots using covalent bonds. They're sharing, and it will look like this when you connect everything together, and then you simplify it. So notice how all of the structures that are already in the table are showing all of those dots. If I want to do it in the same style, I will do the 2 dots that we connected for the hydrogen, and there's 6 dots for the 2 carbons like this. You could also draw it like this to show that triple bond, and then of course the hydrogen. Most of the time they will accept lines instead of those dots, but I like to follow the style of how it's drawn in the question. So this was just 1 point for getting the correct diagram. And then it says, which of the 4 molecules contains the shortest carbon-to-carbon bond? Well, that depends on whether it's single, double, or triple bonds. So this carbon-carbon one has just a single bond, single bond, single bond, and of course ethine that we just draw was a triple bond. So of the 4 molecules, ethine has the shortest carbon-to-carbon bond because ethine has a triple bond between the carbons, making it shorter and stronger than the single bonds present in the other 3. That one was 2 points, actually. 1 for picking the correct substance, and then the second point was for correctly explaining that because it's a triple bond, it's shorter. So that was A and B for that question. Here's another one. A Lewis electron dot diagram of a molecule of ethanoic acid is given below, and the carbon atoms are labeled X and Y respectively, and it says to identify the geometry of the arrangement of atoms bonded to each of the following. So when it says geometry, you're talking about shape. So tetrahedral, trigonal, planar, pyramidal, etc. Be careful not to mix that up with hybridization. I'm going to review that as well, but that is a different type of question or a different answer that you'll get for that. So they also like to, when you're asking these questions, they like to draw it in a way that is not super clear. So for carbon X, it looks like you've got some 90 degrees and a 180 degrees. That's not true because there are 3 areas of bonding around that central carbon. That's trigonal planar. They will actually spread out and all be roughly the same bond angle. A little bit less for this angle actually because of the double bond for the O. But not significantly. So that's for carbon X. For carbon Y, you have 4 areas of bonding around that carbon. So that is, of course, tetrahedral. Now, if it did ask for hybridization, trigonal planar is always sp2 and tetrahedral is always sp3. Linear would be sp. So just be careful there. Okay, so each of those parts, part I and II are each worth 1 point. Part D is really more of a Unit 3 to Unit 6 question. It says, energy is required to boil ethanol. Consider the statement. As ethanol boils, energy goes into breaking carbon-carbon bonds, carbon-hydrogen bonds, carbon-oxygen bonds, and oxygen-hydrogen bonds. This statement is false, and that's because when you are boiling something or changing its state in any direction, you're not breaking those covalent bonds. You're only breaking intermolecular forces. So when you boil ethanol, it's still ethanol. Those carbon-hydrogen bonds or carbon-carbon bonds are still intact. Okay. Okay, so that's why it's false. And that one, part D, was 1 point all or nothing. You had to say it was false because only the intermolecular forces break, not the covalent bonds. Okay, so here's the table again. I'm going to go ahead and fill in the ethine that we got before. Okay, now for part E, identify a compound from the table that is nonpolar and justify your answer. You had a couple options here. It just said to identify one of them. So this one is a polar molecule. You have this SH down on one end, making it uneven. You'll have a slightly more negative side where the sulfur is versus a slightly more positive side on the other end. Same idea with the ethanol. You'll have a slightly more negative end with the oxygen hydrogen. But you could have chosen either the ethane or the ethine as nonpolar molecules. I would just pick one when it says to identify a compound. Just pick one, and you'd say because it has an even distribution of electrons around the entire molecule. Okay, be careful here. A lot of people like to mix this up with polar and nonpolar bonds. So they're not sharing electrons in the bonds per se, or just saying that there's the electrons are shared evenly between the atoms. It might not be enough to get the point for that question. You want to say that either the bonds are nonpolar and in an arrangement that makes the molecule overall polar, or you could say there's a relatively even distribution of electron density around the entire molecule. And that was just 1 point, all or nothing, for that question. And then for part F, ethanol is completely soluble in water, ethanol this time. So whereas ethane thiol, which is this top one, has limited solubility in water and account for the differences in solubilities between the two compounds in terms of intermolecular forces. This is definitely a Unit 3 question, but I'm going to answer really quick. And the reason why ethanol is much more soluble in water is because it can form hydrogen bonds. That OH can help it form hydrogen bonds with water, whereas the SH does not form many hydrogen bonds with water, or as many hydrogen bonds with water. So that's why ethanol is more soluble, because it forms more hydrogen bonds. And that one was 1 point, all or nothing. Okay, so for this, for part D, the Lewis electron dot diagram for C2H4 is shown on the left. In the box on the right, complete the Lewis electron dot diagram for C2H5OH by drawing in all of the electron pairs. So sometimes they'll do this where they'll give you an example and then want you to like repeat the pattern basically. So you'll notice when carbon and hydrogen form a single bond, it's 2 electrons being shared between them. So all of those carbon-hydrogen single bonds. Each carbon, of course, needs a full octet. So you need a, there's going to be a carbon-carbon single bond between those 2 carbons. And not a, this is a double bond in the C2H4. So we just need a single bond for this one, otherwise the left carbon would have too many electrons. Now, I'm filling the octet of the second one, like that. We know oxygen has 6 valence electrons, and so when you draw that out, it has 2 lone pairs. I'm going to put one on the top and one on the bottom, just based on where they put the hydrogen. It makes it a little neater and easier for the graders to see. And of course, there will be a single bond with hydrogen there, so that's another electron pair to fill in that Lewis structure. Okay. So that's for D. Now for E, it says, what is the approximate value of the COH bond angle? So we're looking at, again, if I redraw this oxygen, we know that the 2 lone pairs on the oxygen, and then it will have the 2 single bonds, one with carbon, one with hydrogen. It's hard to show this on a flat piece of paper because it's a 3-dimensional structure. But because there are 4 electron domains, 1, 2, 3, 4, we know that it will be a tetrahedral or a variation on a tetrahedral electron domain geometry. But because if there's 2 lone pairs, we know it's bent. And the 2 lone pairs will decrease this angle just a little bit more than a single lone pair or more than no lone pairs. So you'd say it's approximate value. So don't just say less than 109.5 because there are a lot of values that are less than 109.5. You want to estimate. In this case, something like 104, 105 is acceptable. And typically they'll give a range of values that will earn the point for this type of question. I usually tell my students to remember, like, if tetrahedral is normally 109.5, one lone pair would be about 107, and two lone pairs would be about 104, 105. It's just approximate. But yeah, just 1 point for each of those. All right, now let's move on to some multiple choice questions for Unit 2. This is the C2H4. The HCH bond angles are closest to what? So they like to do this, or they're draw it in an ambiguous way. Remember that any two-dimensional drawing is not going to be perfect because these are three-dimensional molecules. But each carbon has 3 areas of bonding around it. So that makes it trigonal planar. So that would be my your first step, is to always just figure out, okay, how many areas of bonding, what geometry is that? And trigonal planar, of course, has roughly 120 degrees. So the closest one is there. It might be, so this angle here might be a little bit less than 120 because of the double bond and the increased repulsion from those extra electrons, but they're not gonna ask you about that. So the 120 is the closest answer. Okay, so this question, they give us boiling points and ionic radii. So now we're finally talking about some ionic bonding. Based on the data and tables above, which of the following provides the best prediction for boiling point of sodium chloride? So they give you the boiling points for sodium fluoride and magnesium oxide. Sodium fluoride versus sodium chloride, the difference is the halogen. Fluorine is smaller than chlorine, okay, but they have the same charge. So we're dealing with Coulomb's law. Coulomb's law is based on the charge and the distance. Fluorine will have a smaller distance to sodium because it has a smaller radius. So the boiling point of sodium fluoride will be higher because its Coulombic attractions are stronger. So we know sodium chloride has a lower boiling point than sodium fluoride. And then if we're comparing sodium chloride to magnesium oxide has positive 2 or negative 2 charges. So there's a greater charge. So that means that it's going to have stronger Coulombic attractions. So the sodium chloride is also going to be lower than the magnesium oxide because it has a lower charge. So A is probably the best answer. Sodium chloride will have a lower boiling point than sodium fluoride because the Coulombic attractions are weaker in sodium chloride than in sodium fluoride. That's our choice. We know it's not between the two, and we know it's not higher than both, so it's got to be A. Okay, for this question, largest bond dissociation energy, that's the energy required to break the bond between the two. Lithium is probably not going to form bonds like that. Lithium's a metal. Boron, same idea. Boron can be semi-metal. Sometimes it acts like a metal. Sometimes it acts like a non-metal. It's kind of a weird one. But then we have nitrogen, oxygen, fluorine, and those ones are covalently bound. And we have our nitrogen with 5 valence electrons. Oxygen has 6 valence electrons, and fluorine has 7 valence electrons. So fluorine can form 1 bond to another fluoride. Oxygen can form 2 bonds, and nitrogen can form 3 bonds. So that triple bond in N2 is what's going to give us the largest bond dissociation energy. Okay, the geometry of the SO3 molecule is best described as what? So I'm going to go ahead and go through the steps for the more complicated Lewis structures. So for SO3, I'm going to go ahead and add up the valence electrons. Each of them has 6, and there's 4 atoms there, so there's 24 total valence electrons. We always put the least electronegative in the middle. And I just made 3 bonds, so that's 6 electrons I just used up, so I'm left with 18, and I'm going to fill up the valence shells of the outer atoms first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Hey, look, I used all 18, and there's none left over. Once you do that, then you need to check the octet rule. So all of the oxygens have a full octet, but the sulfur does not. That sulfur only has 6. So to satisfy the octet rule, I'm going to go ahead and change one of those lone pairs into a double bond, like that. So now the sulfur has a full octet and the oxygen has a full octet. From here, you could look at formal charges, but I think that we have enough information now to answer the question, because we know that there's those 3 areas of bonding and that there's no lone pairs on the sulfur. So that's going to tell us that it is trigonal planar as your best option. And then what is the hybridization of the carbon atoms in ethine? So ethine, it has 2 areas of bonding, so it's linear overall, and therefore it's sp hybridized.